I'm given a function here, and we're supposed to find some information. First of all, where it's increasing and decreasing, any local minimum and maximum values of the function. To find that kind of stuff, I'm going to have to take the first derivative. So I'm going to look at f prime of x. This is just a polynomial, so I'm going to use the power rule. We bring down the 4, subtract 1. Bring down the 3. 3 times 4 is 12. Subtract 1. So we get that there. I'm going to be looking for where this derivative is positive and negative and equal to 0. So I'm going to have to factor. So I can take out a 4 and an x squared. And if I do, I'm left with x minus 3. So when I set this equal to 0, that's going to find any critical numbers. So I get these possibilities, and of course if I divide and take the square root, the only solution here is x equals 0, and the solution here is x equals 3. And so what I've got on a number line, we would get these values where the derivative is equal to 0. So if it's going to be positive or negative, it's going to have to be on either side of these numbers. So I'm going to get intervals from negative infinity to 0, from 0 to 3, and from 3 to infinity. And I'm going to have to analyze the derivative in each of those intervals to figure out if it's positive or negative. So I can take an interval, I can take a test number, and I'm going to look at 4x squared, I'm going to look at x minus 3, and then I'm going to look at the overall product, which is the derivative. So I'm just going to look at the sign in each interval. So I'm sort of making this sign chart here. We have from negative infinity to 0, we have from 0 to 3, and we have from 3 to infinity. So I take a test number in each interval. From negative infinity to 0, I can take negative 2. I'm going to plug that into these two factors and then multiply the two factors together in the third column. I really don't care what number I end up with. I just care about whether I get a positive or negative. So if I put negative 2 in for x, I get negative 2 squared. That's going to be positive 4, and positive 4 times positive 4 is positive 16. If I plug negative 2 in for x here, I'm going to get negative 2 minus 3. That's going to be negative 5. Again, I really only care that it's going to be negative. And then to get the overall derivative, that's the 4x squared times x minus 3. That's what I've got here. It'll be a positive times a negative, and a positive times a negative is negative. If my first derivative is negative, that means my function is decreasing. Between 0 and 3, I could pick 1 as my test number. I plug 1 in for x. 4 times 1 squared is positive. 1 minus 3 is negative. Positive times negative is negative. That means my function then is still decreasing there. And finally, from 3 to infinity, I could pick 4. 4 times 4 squared is positive. 4 minus 3 is positive. Positive times positive is positive. So my function would be increasing there. So I'm supposed to be saying, where is my function increasing? Where is it decreasing? Well, I found that it's increasing. That's where the derivative is positive. So that's from 3 to infinity. Where it's decreasing, well, that's going to be those other intervals then. So from negative infinity to 0, and from 0 to 3. You probably could just say all the way from negative infinity to 3. It doesn't stop decreasing at 0. When we look at the graph, we'll see what happens there. So I found where it's increasing and decreasing. Now I'm supposed to find any local minimum or maximum values. So a local minimum, that's where a function changes from decreasing to increasing. A local maximum is where it changes from increasing to decreasing. So I'm decreasing from negative infinity to 0 and from 0 to 3. It keeps going down all the way from negative 3 to 3, and then it starts increasing at 3. So it's decreasing until I get to x equals 3 and then increasing. So I'm going to have a minimum. Notice there's nowhere where it changes from increasing to decreasing. It's increasing from 3 to infinity, but then it never changes after that. So I only have a local minimum value. I don't have a local maximum in this problem. So I'm going to have a local minimum at, that's where it changes from decreasing to increasing, and that happens at x equals 3. Now that's where the minimum occurs. To find the minimum itself, I'm going to have to plug in 3 to my function. So I'm going to get 3 to the 4th minus 4 times 3 cubed. So 3 times 3 times 3 times 3, 81, minus 4 times 27. That's going to be 81 minus 108, which is going to be negative 27. So my local minimum is negative 27, and that occurs at x equals 3. Okay, let's look at the next part of the problem. So now we want to find where this function is concave up and concave down. I found the derivative already in the last step, so now I just need to find the second derivative. So to do that, I'm going to take the derivative of this first derivative. So I bring the 3 down. 3 times 4 is 12. I subtract 1, I get 12x squared. I bring the 2 down. 2 times 12 is 24. I subtract 1 and get an x. Now I need to decide where this second derivative is 0 and where it's positive and negative. So I'm going to factor out a 12 and an x. And that leaves me with x minus 2. When I set this equal to 0, I either get that 12x is 0 or x minus 2 is 0. So that gives me places here where the second derivative can change signs, possibly at x equals 0 or at x equals 2. So when I look at the number line, we've got these places here. I've got then intervals around those places from negative infinity to 0, from 0 to 2, and from 2 to infinity. I make a sign chart for these values. I look at each interval. I pick a test number in each interval. And then I'm going to look at these factors of the second derivative. So I'm going to look at the 12x and the x minus 2. And then I'm going to multiply them together to get the whole second derivative. So I'm going to make this sign chart here. My interval is negative infinity to 0. Let me get that better. From 0 to 2, and from 2 to infinity. I'm going to take some test numbers here between negative infinity to 0. I could take negative 2. Then I just plug that into each factor here. 12 times negative 2 would be negative. Negative 2 minus 2 would be negative. And then a negative times a negative would be a positive. And since this is concavity, the second derivative, that means it's going to be concave up there. If I plug in a number between 0 and 2, that might be 1. 12 times 1 is positive. 1 minus 2 is negative. A positive times a negative is a negative, so it would be concave down in that interval. And then finally, something between 2 and 3, I could put in 5 if I want. 12 times 5 is positive. 5 minus 2 is positive. So that's going to be positive, and that means it's concave up there. So I've found some of my information I want here. If it's concave up, I've got that happening from negative infinity to 0 and from 2 to infinity. Right? It's concave up here and here, so that's these intervals there. And then it's going to be concave down where I have a negative second derivative, so that's between 0 and 2. So that's information that I've got there. That's part of what I need here. Then I'm supposed to find the coordinates of any points of inflection. Points of inflection are where the concavity changes. And to see where the concavity changes here, it's concave up, and then it changes to concave down at 0, and then it changes back to concave up at 2. So I have inflection points at x equals 0 and at x equals 2. But points of inflection need coordinates, so I need y coordinates. So I'm going to have to do f of 0. Now remember, that's to find the y coordinate, you have to go back to the original function, not to a derivative or a second derivative. So I have to go all the way back to f of x. And when I plug in 0, I get 0 to the 4th minus 4 times 0 cubed, which is a big fat 0. When I plug in 2, I get 2 to the 4th minus 4 times 2 cubed. So that's going to be 16 minus 4 times 8. 16 minus 32 is negative 16. So my points of inflection, I'm going to put each x coordinate together with its y coordinate. I'm put in 0 for x, I got out 0. I put in 2 and got out negative 16. All right. So when I go to the next page here, I'm supposed to be sketching the graph. Oh, this last part I already had what we wanted there. Let's see, I didn't keep track. What were my points of inflection again? Let's see, let's look back at that. So my points of inflection were 0, 0, and 2, negative 16. Okay, keep track of that for this part here. So if I'm going to sketch this graph, I can make a graph here a little bit. So it's decreasing all the way from negative infinity to 0. Let's see, I didn't keep track. No, that's not what I wanted. All right. Let's see, let me go back here. I didn't write down, so where it's concave up from negative infinity to 0 and from 2 to infinity. It's concave down from 0 to 2. I should have written that on this page here. All right, so we're going to graph this function. So it's decreasing from negative infinity to 0. It's also concave up from negative infinity to 0. When I plugged in 0, I got the point 0, 0. So that's my point of inflection. So 0, 0 is a point on the graph. My relative minimum was at 3, negative 27. I also have a point at 2, negative 16. That's a point of inflection that we had. So down here somewhere we're going to have negative 16. And then negative 27 will be here somewhere like that. And so we're going to have x equals 2. And x equals 3 will be in between. So I've got the point 2, negative 16, that would be down here. What is it wanting to do? And then 3, negative 27 would be my minimum down here. So what we have to have then, it's going to be concave up from negative infinity to 0, and it's decreasing from negative infinity to 0. So it's going to be decreasing, but it's going to be concave up, bowl-shaped up. It's still decreasing from 0 to 3, but it's concave down from 0 to 2. So we can start sketching this in. It was concave up and decreasing over here. Now at 0 it changes to decreasing, and it also changes to concave down, but only until I get to 2, to x equals 2. Now after x equals 2 it's still decreasing, right? It's decreasing all the way from 0 to 3, but it changes to concave up from 2 to infinity. So it's going to go back and do something like this. And then starting here at 3, it's increasing the whole rest of the time. It turns out if we would try to look at the original function and find x-intercepts, we'd set this whole thing equal to 0. We could factor out an x cubed and we'd be left with x minus 4. This has an x-intercept of 4, so it would cross here. It would keep being concave up and cross at 4 and have some sort of shape like that. It's probably smoother than what I've drawn, but my graph would look something like that.